What do a planetary system, our brain, and a pendulum have in common? They are all dynamical systems, meaning they are not static but change as a function of time. When it comes to dynamical systems, it is often easier to explain why they change than it is to explain why they are in a certain state or position. For example, we can explain very well how the speed of a pendulum changes, so how it accelerates. All we have to know is the length of its string, how fast gravity is accelerating the pendulum downwards, and the position of the pendulum. A shorter string will lead to a faster acceleration, and a lower gravity force has the opposite effect. The effect of position on the pendulum's acceleration is also straightforward. At its highest point, the acceleration is also at its highest, and the ball is accelerating close to a freefall scenario. And at its lowest point, where the ball has reached its maximum speed, the acceleration is 0. Now that we have established how the pendulum changes, we are set to explain the pendulum's position. To describe the pendulum's position as a function of time is a lot more complicated than it was to explain the acceleration. That is because the position of the pendulum depends on how fast it accelerates, but its acceleration, as we established, also depends on its position. We will call this yet unknown position function theta. And if we were to find it, then we could predict the pendulum's movement, which might not sound that useful, but in another scenario, the pendulum might be a meteor that is heading towards Earth. And in that case, it would be pretty neat to predict where it might land. Before we get into any predictions, let's take a look at the effect of position on acceleration. Acceleration is the second derivative of position, so it is indicated by the curvature of the graph. We can see that when the pendulum is at one of its highest points, the curvature of the graph is maximal, meaning the acceleration is at its highest. Whenever we are dealing with change that is dependent on position, we can use differential equations. They describe how the derivatives of a function, so how it changes, relates to the function itself. Here we have the differential equation for the pendulum's acceleration. It describes what we have already explained, namely that the pendulum's acceleration depends on the length of its string, the gravitational force, and its position. Now, why is the coupling of position and acceleration making it so hard to explain where the pendulum is at? If we would try to reconstruct the path or position of the pendulum manually, then we would have to check before every step what our acceleration will be towards the next position, based on our current position. For that, we can use our differential equation, where we plug in our position and get the acceleration in return. Now you could say this sounds like a reasonable approach. Let's just check every 10 milliseconds or so what our acceleration is and infer from that our speed and then position. And you would be right. This approach can be very useful in cases where it is too hard to calculate the actual function of position. What you can see here is the approximated path of the pendulum, which was generated using a step size of 1 millisecond. And it looks really good. But you might already see the problem of this approach, because even if we take very small steps, we are not considering how the acceleration changes between the beginning and end of our steps, since we only calculated the acceleration at the beginning. So it is very likely that we land at the wrong position, where we get wrong acceleration information, or at least it is from the wrong position, which means we step even further away from the path, and then this cycle continues until we have wandered off completely. This problem gets very visible when we increase our step size to 100 milliseconds. The only way not to wander off when using this approach is to reduce the time between our steps to 0. But that would also take infinite computing time. To avoid this rather long waiting time, we can try to actually solve the differential equation that we used to calculate a few acceleration values. If we solve the differential equation of the pendulum, then what we get is the position function, or the path, that at every step is in line with the changes that it provokes. So if we take the second derivative at any point of our function, this value will be equal to the acceleration that we could calculate based on our position using the differential equation. Here you can see the solution for the pendulum's differential equation. It looks really complicated, and it is even more complicated to calculate, which is an ongoing theme for most differential equations. So we will not go into detail on how to solve any of them, but instead look at the general cases and then introduce a nice way of visualizing them. The general case of the pendulum's differential equation is just a function that's in relation to its derivative. It is, however, also possible that the change depends not only on position, but also on time. We would need this kind of differential equation for a dampened pendulum that slows down over time. Since we are trying to model the brain as a dynamical system, we don't have to bother with this additional time dependency, because our neurons don't behave differently just because an hour has passed. For practical purposes, we often leave out the of t part of the function and instead just write f or y. But this notation has the exact same meaning and still stands for a function that is dependent on time. We can visualize differential equations as a phase space. In the one-dimensional case, it's called a phase line. On the x-axis, we have the possible states of a dynamical system, or the values that a function y can take. How the system changes when it's in a particular state, or how the function y changes at certain values, is realized as vectors that point in the direction of change and indicate the magnitude of change, usually through their length, but color also works to give some intuition. So what we have here is a mapping of vectors to each function value. What is responsible for this mapping is our function f, that takes values of another function y and returns a field of vectors. Because it gives us a field of vectors, we call this function a vector field, referring to what it's mapping to or returning to us. Before I reveal what f actually is, take a second to look at the vectors it returns for some values and then guess what it could be. If we look at the vectors, we notice that their length or magnitude increases when the function values are getting bigger. And when the function values turn negative, the vectors change their direction as well. This calls for the identity function, meaning a certain function value and its associated change are identical. So if we are at the function value 0, then the change at that position is also 0. A solution to our differential equation is every function that follows the flow of the vector field. Just to be clear on what a function is in our scenario here, it is a path that is taken on the x-axis as time goes on. For example, we could have a path where we are not walking at all, but just sit in one position, for example at the number 4. The function of this path, so y of t, would then be just 4, so independent of time. This function is obviously not a solution to our differential equation, because it is not equal to its derivative. So the derivative of 4 would be 0 and 0 does not equal 4. If we want to know what a path or function that is in accordance with the vector field looks like, we can imagine a small particle that is transported by the vectors with different directions and at different speeds. We can imagine them like winds flowing in various directions. If we track the particle and its position over time, then we get the classical graph of a function that solves the differential equation. You might recognize this function. It's the exponential function, although shifted up a bit. And that makes a lot of sense, because the exponential function satisfies the condition of being equal to its derivative. Let's move up to two-dimensional differential equations. In 2 dimensions, the change can happen in 2 dimensions, so we need 2 equations to determine how much we change in the respective dimension. How much we change in each dimension also now depends on two coordinates, x and y. We can transform these equations into a vector field notation, where the vector field v takes the coordinates x and y and returns the respective vector. Since our vectors are now two-dimensional, we need two functions, f and g, that determine the x and y coordinates of the vector. Let's start with a simple example, where the change in the x dimension only depends on x, and the change in the y dimension only depends on y. If we are now at the position x equals 2 and y equals -1, then we get a vector that indicates a change of 2 in the x dimension and a change of -1 in the y dimension. If we repeat this for a few more coordinates, then we get a nice illustration of our vector field. Let's now consider a more complex differential equation, where the change in each dimension depends on both coordinates, so x and y. Just like in one dimension, we can imagine a particle that flows along the vectors to get an idea of what a solution to our differential equation might look like. This path, or the function that describes it, would satisfy our differential equation. That means that if we choose any point in this function or path and take the derivative in the x dimension, then we get x plus y divided by 2. And if we take the derivative in the y dimension, then we get x minus y divided by 4. We can take the derivative in different dimensions because the function can change differently depending on which dimension we are considering. Now finally, let's connect what we have covered today to the brain. In the beginning, I said that the brain is a dynamical system, and so it should be modeled as such. For that, we can use a differential equation that describes how the voltage of a neuron changes, and how neurons behave under different conditions. To now observe the behavior of a neuron, we can again imagine a particle in place of the neuron's state, and see how the particle and so the neuron's state changes over time.